Hey everyone, my name is Derek Arns. I'm going to be giving a quick little demo on how to protect yourself from reentrance vulnerabilities in Solidity. So to get started, I have Remix here open. I'm going to make the assumption that you know how to use it. If not, feel free to go out to my website and check out the demo or just check it out on YouTube. All of this code is also available out on GitHub, so feel free to hit that up at GitHub with Derek Arns. So the first thing that I'm going to do is go over the vulnerable contract. And so let's take a quick little look. So this contract, we'll just call it vulnerable contract. It has a list of balances or a mapping of addresses to the amount of ETH passed in. We're calling it balance. Here we have a little function just to allow senders to pass in their ETH. And then we just have a simple withdraw function. So this withdraw function is just going to check the balances of the address or the sender coming in, and then we're going to make a call out to the sender and give them their balance, and then set the sender's balance to 0. And this is really where the vulnerability comes in. We're making an external call out to the sender, and that is, in theory, could be another contract that's making a call back in, and we'll be checking that out in just a second with how the attacker would do that. And then here we just have a little helper function just to check the balance of the contract. So how could what would an attacker contract look like? So here we have the attacker contract, and it's just going to have a reference to the vulnerable contract's address when it gets constructed. We have a fallback function here, so this is going to be the function that gets called when this vulnerable contract does this message sender.call. Because none of the functions get matched, it's going to hit this fallback and send in the ETH that was from the balance. And here's where it's allowing us to call back in. So we're saying, hey, if the vulnerable contract has a balance of more than 1 ETH or 1 ETH, we're going to try to withdraw some more. And so we have a function here to do the attack. And this attack function is just going to allow anybody that calls this contract to pass in 1 ETH and be able to withdraw all the ETH from the vulnerable contract. And then we just have a simple balance here to check the address or to check the balance of this contract. So the first thing that I'm going to do is just kind of come over here and compile these contracts real quick. Go over here, select the first account, and the first thing that we'll want to do is deploy the vulnerable contract. Once we have the vulnerable contract deployed, copy its address, come over to the attacker contract, paste in the address here, deploy it as well. So now we can see that we have the vulnerable contract and the attacker contract out there. And so while I'm still on this first account real quick, I'm going to just deposit a couple ETH. So if we come in here and select 3 ETH and do a deposit, we can see that the deposit was successful. If we check the balances here, we can see that this contract has 3 ETH. So what I'm going to do is come over here, go back up, go to the accounts, switch accounts, and set this to 1 ETH. And we're going to go into the attacker contract here and click the attack. And we can see that the attack was successful. If I check the balance here, you can see I now have 4 ETH. And if I were to look in the vulnerable contract and check its balance, it now is at 0. So that's how an attacker could attack a vulnerable contract. So the next thing that we're going to want to do is take a look at some ways to secure the vulnerable contract. The first thing that we can do to secure a vulnerable contract from reentry is going and using the OpenZeppelin reentrance guard. This is one of the ways I like because the code has been viewed by a lot of smart people. It's used widely, so I know that it is probably a little more secure than if I had to roll my own, but it's not too hard to roll your own either. So the first thing that we want to do is just say that this contract is a reentrance guard. That's going to give us the ability to add non-reentrant modifiers to our functions. And this contract is going to do the exact same thing. We're just going to have a mapping of addresses to ETH. We're going to call it balances. It's going to allow the sender to pass in ETH. And then it's going to be able to have those senders also withdraw that ETH. And here's where a lot of the changes are going to come in. So the first thing that we're going to do is rename it from withdraw to withdraw untrusted. This is going to allow any other contracts out there and to remind us ourselves that, hey, this is going to be making an external call, and that external call can't be trusted. And then here's where we're using that non-reentrant modifier. So if they do try to enter the method again, the Open Zeppelin reentry modifier will reject that transaction. And here's where we could also have made the change, and instead of adding the non-reentrant modifier, we could have just swapped the behavior. So before in the vulnerable contract, we had, hey, we'll make a call from, we'll call the sender and then clear out their balance, to now in the secure contract, we're going to clear their balance first and then make the call to the sender. This allows us to do this check here to require the balance, and that way if they were to make another call in, they'll have a 0 balance this time. And then again, just a quick little function to check the balance of this address. The attacker contract is going to look exactly the same as it did before, only now it's going to have a reference to the secure contract, and it's going to do the exact same behavior of making a call to attack and hit the fallback function. So we will do a quick compile on these as well. And from the first account, we will select the secure contract now, hit deploy, grab its address, go to the attack, paste in the secure contracts, and while we're still here, let's add a couple ETH to the more secure bank account. And if we check the balance here, we can see that the balance is 3. All right, now let's switch accounts and go to 1 ETH here and go to the attack contract and try to attack it. So now when we try to attack it, the transaction is actually going to get reverted. Let's take a quick little look at why that is. So the reason that this is getting reverted now is primarily because of the, non-reentrant. So we can take a quick look at that code out here in Open Zeppelin. The modifier non-reentrant, we can see that it's going to require the status of not entered. And so the first call is going to get a status of entered, and it's then going to make that function call. And by the external contract trying to re-enter here, it's now going to have a status of entered, so it's going to fail this required check here. And because of that failed required, it's going to roll that transaction back, and then we get this required, which is requiring that the sent was successful. And because it wasn't successful, we can see here the reason that it failed was we were not able to send the ether. So if we go back over here real quick, we can see that the balance of the attacker contract is still 0, and the balance of the secure contract is still 3. And that is one way to secure your functions from the reentrance vulnerability. Thanks.